everybody, today we're going to be talking about natural language processing and more specifically about word embeddings. Now we'll start at the beginning. How do we represent text? In week 2 you've already seen a few ways of loading text into variables. We're going to be quickly repeating these and going one step beyond that. Okay. So what is text? Text, if we look at the dictionary, is all about meaning. Right? The implied or explicit significance of text, its purpose. So when we do NLP or natural language processing, we need to find ways that will enable us to not just represent the text, but represent the text in a meaningful or semantic way. So a common answer would be WordNet. WordNet is a little bit of an older system of representing text, but basically it has a taxonomy that has synonyms, is as, is a, relationships, etc. So here in the photo you see a small excerpt of WordNet. This is the word book and all of the words that surround it. Right? We have record, book, volume, ebook, record, reserve, product. So all of these vertices connecting the nodes will have relationships such as is a, which we call is a. This is what we call a hypernym. Okay. So a hypernym basically is a word with a broad meaning that constitutes a category in which the word that you're talking about belongs. So in the case of panda, here, not that it's confusing that because we use the pandas library. Here in Python I have a short code snippet that looks for the hypernyms of the word panda. Okay, so what do? We use the library NLTK, Natural Language Toolkit, and we import WordNet. We call it VN. So in this case, panda is what we call a syn set of the word that we refer to, the string panda. Now we're getting all the hypernyms of panda and we can list them. And the results are here on the left. So for instance, we have carnivore, placental, mammal, vertebrate. These are all categories or hypernyms of the word panda. Okay. So this is one of the applications that we can do with WordNet, but there is a good number of others. For instance, if we can also look not just for hypernyms, but also for synonyms. So of the word good, for instance, WordNet will give us the following synonyms. So these kinds of graphs are knowledge graphs are quite useful for helping us meaningfully represent words. However, it is a good resource, but there are some problems with this. What if we were to have a new word that people start using? There are some examples. Okay, these don't really seem like new words to me, but adding a new word, it's basically impossible to keep this up to date because you'll need manual annotations of this. It misses a lot of nuances, right? If I look for synonyms of adept, expert, good, practice, they're all synonyms of good, like we saw on the previous slide, but they are, in a nuanced way, they all mean something slightly different. So we can't really capture this with WordNets. Okay. So it requires a lot of human labor to adapt and create. It's quite hard to compute word similarity. So as I was saying before, good and adept, how similar are they? Are they just the same? How do we capture this nuance? WordNet doesn't really do that. So the vast majority of rule-based and statistical NLP regards words as atomic symbols. That means they're all discrete symbols and we don't know how similar they are, how related they are, except for the defined relationship, synonym, hypernym, etc. Okay. So in what we're going to be seeing, this is going to be changed. Okay, let's start with how to represent words. We take a step back here. First, one possible way is a one-hot representation. In a one-hot representation, we basically have a column for each word in your dictionary And then you just put 1 for the word it is. So each word is represented by a vector with 1, 1, and all the rest are zeros. Okay. So you should know that the typical vocabulary that we use when we're talking is about 20,000 words. Okay. If you're a very eloquent speaker, you might have a big vocabulary and it goes up to 500,000 words. If we're looking at the words that are used in the Google Web dataset, it's 1 terabyte dataset, we're looking at 13 million words. So even if you're just an eloquent speaker, each word is going to be represented by 500k tokens, which is an enormously sparse representation. There are so many zeros. Right. So there's a lot of information that we store that we don't really need to store. So it is, I must admit, it is the simplest method to implement. It can work pretty good, depending on your computational resources. As you know, it's very sparse. It would require a lot of memory space. It is unordered, so the context of the word is lost. Which word came first in the sentence? And the vector representation is in binary form. So we have no frequency information, like how often does this word occur in the corpus or not. Some of these problems we'll fix in some of the next methods. For instance, bag of words. How do we represent a sentence in bag of words? Dataset 1 is 1 sentence. I went to the movies yesterday. D1, we represent D1 as I went to the movies yesterday, and all the rest is going to be zeros. Again, you basically have each column is 1 word in your dictionary, so it's still a sparse representation. However, we have some more information because here we're taking frequencies or occurrences into account. Let's have a look at D3. Yesterday I went swimming and I ran. Now the word I occurs twice in this sentence, so that is captured by our model. We have slightly less zeros because a whole sentence is condensed in 1 row. We don't really have 1 row for 1 word. 1 row is 1 sentence here. So we have a little bit more information, but it's still quite a sparse representation. So, high dimensional, very sparse. It doesn't capture word order yet. Something is good but expensive, or something is expensive but good. Same representation in bag of words, but different meaning. So these are the things that we're going to try to take into account with more advanced models like attention networks, BERT, etc. It can't capture similarities, right? It can't really say if we have boy, girl, giraffe, all these words, how similar are these words? We don't really know. Okay. This is something that in later word embeddings like word2vec, Glove, we will be able to do. Alright, so let's move along. We had 1 hot representation, we have bag of words. There is also TF-IDF or term frequency inverse document frequency. So the motivation here is that words that appear in a large number of documents might not be significant, so they get a smaller weight. Think of the word I, and, a, do. These are words that occur really often. So, contrary to what you might think, they actually confer very little meaning. Okay. On the contrary, I use a rare word, aardvark, cryogenic. It's very specific, so if a rare word like this occurs, we need to make sure that it gets extra weight in the sentence because most likely you're talking about this word and it's important. So, how do we calculate this? So here's an example. It actually looks similar in the sense that we have again a column for each word in our vocabulary, high dimensional representation, but now we don't have 1s and 0s, we have ratios of frequencies. Ratios of frequencies. How do we calculate this before we look at an example? The term frequency is the number of times a term appears in the document that you're trying to represent. divided by the total number of words in the document. Okay. Inverse document frequency is the logarithm of the number of documents you have, and the number of things you're trying to represent, divided by the number of documents that this term appears in. Okay. When we have TF and we have IDF, we can just multiply them. So the higher this TF-IDF score, the rarer the term is, and vice versa. Because this will give you an indication of how rare the term is. Okay. So there's some variations of these implementations, but in essence, the principle behind it is typically the same. For instance, we want to know the TF-IDF of the word cat, and we have a document with 100 words and cat appears 12 times. Okay. In the total corpus, we have 10 million documents and the word cat appears in 0.3 million of those. How do we go about this? Okay. TF, term frequency of cat. Okay, look back at the previous slide. Term frequency is the number of times the term appears in the document divided by the total number of words in the document. Okay, so we have a 100-word document and cat appears 12 times, so our TF is 0.12. Now, let's calculate the IDF, which is the logarithm of the number of documents divided by the number of documents that the term appears in. So we have 10 million documents, and only in 0.3 million does it occur, so our IDF is 1.52. So our total resulting TF-IDF weight is 0.182. All right, so let's have a look at the next step, which has been quite popular since about 2012, which is dense vector embeddings. If you've noticed, all these, however well they might work or intuitive they might seem, they have a huge number of categories, basically at the lowest case, 20,000 for a small vocabulary, 20,000 columns. Dense vector embeddings are of a low dimension. That means they're not sparse, they don't have a huge amount of zeros, and hence they'll be computationally a lot more efficient to work with. All right, to understand word vector embeddings, we need to look back at John Rupert Firth, who basically posited the distributional semantic hypothesis. He said, "You shall know a word by the company it keeps." What does this mean? Words that occur in a similar context tend to have a similar meaning. This was formulated actually by Harris already. So word embeddings leverage on this distributional semantics hypothesis basically by saying that if words occur in a similar context, they probably have a similar meaning. Here's an example. I enjoyed eating pizza at the restaurant. Let's look at a word that we're trying to represent, pizza. The company it keeps, or the context, would be all the surrounding words, typically with a window length. I enjoyed eating pineapple at the restaurant. Does it have the same meaning? It doesn't have the same meaning. However, because it appears in exactly the same context, it actually has some properties similar. It's both something that you can eat at a restaurant. So these two words aren't entirely, they have a different meaning, but they aren't entirely dissimilar in the fact that they're both foods that you can eat at a restaurant. So this principle is what will allow us to train our word embedding model. Okay. But first, let's talk about co-occurrence matrices. So a co-occurrence matrix X is something that allows us to integrate the neighboring words when representing words. So we have two options here. As I mentioned before, we can work with looking at a window, let's say 2 or 3 words around your word, or you can look at the entire document that it appears in. Okay. So the first, if you have, the first that I mentioned was the second one here. If you have a window around each word, it captures both the syntactic and the semantic information. If you're looking at the whole document co-occurrence, it often leads to what we call a latent semantic analysis. So let's have a look at window-based co-occurrence. In case our window length is 1, this is just for ease of explanation. More common is window length 5 to 10. And we're looking at symmetric, so we don't care if the word next to it is before or after. Let's have a look at how we would calculate window-based co-occurrence matrix on this example corpus here. So, I like deep learning, I like NLP, I enjoy flying. This is our matrix. Our data set. So, how to represent this? We will have all of the words in our corpus as the column and row headers. Now, each time words co-occur, for instance, I and like, we will add +1 count. Like and deep, +1 count. Deep and learning, +1 count, etc. And that's how you form this window-based co-occurrence matrix. Now, this is not perfect yet, because again, when our vocabulary becomes big, our matrix becomes also very big. So again, we are dealing with high-dimensional representation, which requires a lot of storage, hence in time also requires more computational memory if you're going to be running deep learning models or something. So basically, also, if you do classification models, then it can really have sparsity issues again because of these many zeros that occur. So the models that result from this are less robust. The solution would be to create low-dimensional vectors. So the idea is to store the most important information in a fixed small number of dimensions, so a dense vector. Typically, these vectors have around 25 to 1,000 dimensions, so way less than our 20,000 in our dictionary. Now, if we have our co-occurrence matrix, how do we reduce the dimensionality? Well, we can use a dimensionality reduction algorithm, such as singular value decomposition. All right, so how does singular value decomposition work? Well, we have our co-occurrence matrix X. And that X, we will be splitting up in 3 matrices, U, S, and V, whereby U and V both are unitary matrices. Now, remember from your math class how SVD is actually, singular value decomposition, SVD, is actually done. It's not my intention here to go into the maths of this process because it will involve eigenvectors, etc. But it is important that you know the final result of the SVD. So in this case, we have U and V, which are unitary matrices. That means that U multiplied by the transposed U equals an identity matrix I. Okay. Same goes for V. Now, S is actually a non-negative diagonal matrix. That means that it has all zeros except for the diagonal, and on the diagonal are non-negative values, which we call the singular values. Okay, R is the rank of S. It is a square matrix. We are interested in representing our matrix X for each we have here, right? Okay. Now, it can still be that this representation is of a high rank. Therefore, we are going to reduce the rank and create an approximation of X hat, which is the best rank K approximation to X. So we're reducing the rank from R to K. Now, in doing so, we're going to basically cut off part of this U and cut off part of V as well. and of S. Now this new U will be our new representation. In the U matrix, the most important prominent representation really is the ones that occur first on the left side. So that means we're basically going to use the first k rows of U to represent our data. Okay. How does this look more concretely? If we're doing this in Python, we can quite very easily get a singular value decomposition. We use a NumPy package called linalg, linear algebra. If we have words that we're representing, this word list for instance, then we can create a co-occurrence matrix X. This is done by hand. You can script it if you'd want. Then from this linear algebra library, we're calling the SVD function and basically feed it X and say we want U, S, and V. That's it. That's what does the SVD. So it's pretty quick to do this in Python. Okay. Now, if we're going to be plotting this, as I said, we're going to want a lower rank approximation of U. And basically the only thing we do for this is reduce the dimensions of U, cut off part of the matrix. In this case, we could possibly only use the first two dimensions. The first column, the second column. If we use those two, we basically get two coordinates for each word. And we get plotted like this on the graph. Now, ideally, if you have a huge matrix, we would see that words that occur close together on this graph have a similar meaning in real life. So obviously our corpus is too small to see this, but that is how SVD works. So just to recap, we split our matrix X into U, S, V. S being the non-negative diagonal matrix, U and V being the unitary matrices. Then we basically cut off part of U, and U is the one we're interested in. U is what we're going to be using to represent all of the words in X. Okay. Right, so in the end, I showed you on the graph we can use the first two dimensions, first two columns, but we can really use as many as you want. This is a hyperparameter. It's a value that you decide on, and perhaps you test on which value works best for your particular data. Okay. So the resulting model is that a word has a dense vector representation, which might look, for instance, like this. It is basically a list or a vector of doubles. Okay. Now, if we have this multidimensional list, quite often dimensions will be between, I don't know, 100 and 1,000. So how do we represent that? Because I want to evaluate how well my model works, but how am I going to represent a 1,000-dimensional vector of each word and see how similar they are? Okay. So there's a technique that you'll see is very often used in neural networks and word embeddings. It's called TSNE, or T-distributed stochastic vector embedding. It was developed in 2008. You see one of the big names occurring here, but Van der Maten was the guy who led this development. So it's really well suited for the visualization of high-dimensional data sets. Now, I am emphasizing visualization here because this has nothing to do with creating the embeddings, right? What we just did is that we created a vector embedding for each of the words. Now we have all these long multi-dimensional representations and we want to somehow visualize them, but we can't really visualize hyperspace. So what we do is we use a technique called TSNE. TSNE is a way to project multi-dimensional vectors into 2D space. Okay. So how does it work? Step one, the TSNE constructs a probability distribution over pairs of high-dimensional objects in such a way that similar objects have a high probability of being picked first, while dissimilar points have an extremely small probability of being picked. Okay. You understand that? So we basically say similar objects will have a high chance of being picked first, and dissimilar points have a small probability of being picked. Okay. Step 2, TSNE defines a similar probability distribution over the points in the low dimensional map. So also in this low dimensional map, basically we're saying that similar objects should have a high probability of being picked. Dissimilar objects should have a low probability. Now we have two probability distributions. How can we make sure or optimize that two probability distributions look similar? We minimize the distance between these two probability distributions, and we can do that using KL divergence or Kolek-Lieber divergence. You may have seen this before. If we have probability distribution A and we have probability distribution B, how are they the same? How similar are they? One way to measure it is by KL divergence. Okay. It is a very often used metric when we're optimizing neural networks, for instance. Okay. So it's often used in the loss function whenever we're comparing two distributions. Okay. Okay. Now, this TSNE, when it's building, it optimizes such that similar points in the high dimensional space are still close by in the low dimensional space, and vice versa. So that's exactly what we want. If two points are far apart in this high dimensional space, you know, we can calculate Euclidean distance between high multidimensional points. They have their, let's say, 2 points using Euclidean distance are far away in this high dimensional space. Then when we project them in a 2D space, these 2 points should still be far apart in the 2-dimensional space. That's basically what it's optimizing for. So, how does it work? In Python, super easy. You just call the TSNE function. You have some you have some parameters. For instance, we do principal component analysis to do the first initialization. You set the number of iterations it's optimizing for, the number of components. So that means we're going to project in 2-dimensional space. Some random states so that we always have the same results. It's sort of a seed. Now and then we're just going to fit the transform into the TSNE model. Okay. How does this work? If I'm just have an animation here that visualizes an animation of how points in the multidimensional space are optimized. So we have similar colored dots here are similar points, similar words, or whatever you're trying to visualize. And we'll see, so the objective is that points with similar meaning or color are projected close to each other in the space because they are projected close to each other in, not projected, they are close to each other in the multidimensional space as well. Here we go. So you can see how this 2-dimensional space adapts until it optimizes for distance between similar points. We'll be practicing this a little bit in the lab this week as well. So when we do this, when we calculate our word factors using a singular value decomposition, we might have, I don't know, 500 dimensions. How do we then, if we then project these 500 dimensions into two-dimensional space using TSNE, we can actually see if the model makes any sense. For instance, this is a paper from Roth et al. In 2005, and they built indeed a similar semantic word embedding model. And when they project it into two-dimensional space, this is really interesting. They see that similar words, chose, choosing, occur close together. Take, taking, took, stole, steal, stolen. Isn't that super interesting? It means that the model, without telling it that these are conjugations of these words, learns that these words are super similar. I think that's super interesting. And TSNE is a great tool for having a peek into this multidimensional space. Here's another example. We'll see that teach and learn hopefully go together. Yeah, janitor and student, I don't know what that's about. Bride and priest. So there's a lot there that we can see. And it's very interesting to study these embedding spaces. So another way of representing these multidimensional word embedding models would be through graphs like the dendrogram that's depicted here. Now, there's still some problems with this singular value decomposition problem, and that is related to the computational costs. So basically, you have an exponential cost in terms of computation when n is larger than m. So when we're dealing with millions of words and documents, this gives you a bad situation. Okay, it would entail that actually doing this decomposition will be taking a really long time. Okay, so how do you represent or incorporate new words or documents in your model? You'd have to rebuild the model from scratch. Okay. This is a different type of learning than other deep learning models. Then deep learning models, they really shouldn't be in other. It's not a deep learning model. So how do we deal with word embeddings? Why don't we directly learn our low dimensional word vectors? With low dimensional, I mean like 500 dimensions or something, like these SVD embeddings. Why don't we directly learn them instead of first doing a huge SVD, which is a computationally really heavy operation, which is hard to incorporate new words, and it's basically hard. So why don't we directly learn these low dimensional word vectors? And one potential solution is word2vec, which has a lot of examples over the traditional methods. Here again, we see where we started from today. We had the one-hot encoding. We have the word embedding, where each word is a point in n-dimensional space. N can be about 100 to 1,000. They say 300 here. I think it goes until 1,000 these days in literature. It can be trained using a big data set. It's not a huge vector like one-hot that has to be the size of the entire vocabulary. It doesn't have many zeros. It basically represents each word as a limited 100 to 1,000 dimensional vector. Okay. In addition, word embeddings use the context information, so the co-occurrences, which according to the distributional semantic hypothesis have an influence on their similarity and meaning. Right, so the first usage of the word embeddings was in 2003 by Benjo et al. So they proposed this new model for distributed representations of words using neural networks. So that's really, when I say embeddings, this really refers to the neural network approach. When I say dense word representations, it refers to everything that comes before, including SVD. Now, in 2008, this became more mainstream, and Colbert and Weston proposed a unified architecture for NLP, but it wasn't until really 2013 that it really became popular by a paper called Word2vec, or which had the word Word2vec in it, by Mikolov. And it has pre-trained word embeddings that are making NLP tasks so much more easy for us. So Word2vec is what we'll talk about a little bit. Instead of capturing the co-occurrence counts directly, Word2vec is trained by predicting the surrounding words of every word. So we're dealing with neural networks here, so we can do predictions. Our training objective is to maximize the likelihood of the context, so predict the words that surround it, given the focus word. Here we're predicting the likelihood of I given the word pizza, the focus word. We're predicting enjoyed given the word pizza, predicting the word restaurant given the word pizza, etc. So you're predicting the likelihood of each context word given the focus word. So really, the only thing you use to train your neural network, you always need an input. The input here is pizza, and the output can be enjoyed. Yes or no, right? So you train the network by giving it these pairs: input word, output word. That's pretty much it. So an example, again, we can look at this entire, you can look at this entire sentence. Given a focus word pizza, we're predicting all the words around it, given here at least a window of length 3. We can move to the next word after. So the training happens like this: you choose a focus word, then you move to the next word, the next word, the next word, and that's how you're going to create all your training pairs. So here again, we're now given the focus word at. We are predicting all the words that occur around it in its context. And I see we're still trying to predict I, so that means the window length is at least 4 here. So we have an input word and an output word. And our training samples are just pairs: input word, output word. And that's it. So the cool thing about the word-to-vec model is it's a super simple neural network. It's not even a deep neural network. It has one hidden layer. And it allows us to not count these co-occurrences, but predict the co-occurrences. Okay. Another example. We have the quick brown fox jumps over the lazy dog. The training samples here, we have a training window of length 2. Focus word the. Our input pairs are the quick and the brown. Focus word quick, input words quick the, quick brown, quick fox. We slide again. Focus word brown, so the input pairs become brown, fox, brown, jumps, brown, quick, brown, the. Okay. Then we shift one over again. Fox brown, fox quicks, fox jumps, fox over. Okay. So great. Notice that we're not counting the here because the window length equals 2. So this context window is going to be always around the focus words, which you see illustrated here as well. When we're training, we have 2 architecture options. Both are one hidden layer. It's continuous bag of words and skipgram. Okay. The latter is a little bit more popular. Skipgrams predict the surrounding context word given a center or focus word, which is what I was just showing you the input-output pairs for. If you're doing continuous bag of words, predicting that basically predicts the exact opposite. So in skipgrams, we have input, focus word, and context word. And in continuous bag of words, basically we have context word, and then we predict the focus word. Since it's a pretty symmetrical architecture, the difference between the two is really minimal. Okay, you're going to be talking a little bit more about SIBO in Prof. Sujanya's course. So we focus on skipgram. We have one focus word or input word, one hidden layer, and then we predict our output words. Okay. This is the representation you'll find everywhere on the web, and it really confused me when I first saw it a few years ago, because it looks like you're feeding it all the output words at once. That's not correct. You're actually feeding it one input word and one output word at a time. Okay. But the representation of the words is a one-hot representation when you're inputting it and outputting it. Okay. So hopefully that is not confusing. Just know that you're always feeding it one input word and one output word at a time as a pair. Yeah. Right. So how does it work? We have, as I said, a one-hot vector, your input vector, which will be the focus word, one hidden layer, one output layer. It's a softmax classifier, so just predict the class. and it'll predict class probabilities for each of the output words. And that's it. Super simple, very quick to train as well. Now, to train this neural network or set the weights, we can decide the window size. That is depending on your dataset size or the quality of your dataset. You need to set or decide the embedding size, which is the size of your hidden layer. How many nodes are there in the hidden layer? And that will determine how big your vector is that you use to represent your word. What's the size of your vocabulary? Now, often when you have a look at the frequency of occurring words in your dataset, you'll see something like this. Okay, and this goes on for a really long time. So what do we have here? The frequency, and here we have each word. So what does this mean? It means there's a few words that occur very, very often, and then there's a few words that appear like only once. There's no use of, well, there might be use, but typically we do some sort of cutoff. Okay, you limit the number of words that occur, that you take into account, and all the rest you replace by something they call an UNC token, unknown, because it makes your input representation, the one hot vector, a lot smaller, so it can help train the model. Okay. If you don't have much information about the words, your model, or because they do not occur often, your model is not going to be learning too much useful about them anyway. Okay. So choose the size of your vocabulary. Also, some words like the or a may be omitted because they typically don't contribute too much information. So these are some, as any neural network will need to set some hyperparameters when we're training it. Okay. Then we have our training objective, which is softmax cross entropy. Now, this can be hard to compute. So there is a little bit of a way around this, which is what we do when we're training Word2Vec, and it's called negative sampling. This saves us from calculating the cross entropy for the loss function. Okay. How does negative sampling work? So the original training objective, the cross entropy, is approximated by a more efficient formulation. What do? Basically, we implement a binary logistic regression to classify between data and noise samples based on the given embedding. So how does negative sampling work? Negative sampling basically replaces the objective. Each time you perform a training step, you run a classification model, which is a simple binary logistic regression. You input an input and an output word, and you see if they match or occur in the same context or not. To do this, you need to feed it both matching words and non-matching words or negative samples. That means we feed it, for instance, in this case, the and cat would be positive samples, the and pushed positive samples, but cat and glass may never occur in the same context. Okay. So if we feed it words in our new embedding into this very quick classification model, it should, based on the embedding, be able to predict if they occur together or not. Because a good embedding should represent that words that appear in a similar context have a similar meaning. Okay. So in fact, how do we get our embeddings out of this model? Our embeddings is basically very simply our hidden layer weight matrix. So this becomes a vector lookup table. You feed an input word, and you just calculate what's happening in the hidden layer, and that's it. That is your word embedding representation. So basically we're using the latent variables of the word2vec model to represent our data. It's as simple as that. And when we're doing the negative sample as the objective, we're using the newly trained embedding, and we're seeing if based on this embedding we can classify between input and output words that appear in the same context or not. This is way quicker than if we were to do it using the traditional cross-entropy loss. Okay. So the results of running word2vec is it's very fast, it's usually accurate predictive model, means it can be used for many other tasks. It correctly captures semantic content. It's very popular. We'll demonstrate actually the capturing of the semantic content in a little bit. There's lots of pre-trained models available. That's very cool. It's super fast to train, especially using the negative sampling, and it's very easy to use using Python GenSim library. I've written a paper on using word2vec to represent music myself. I'll talk about it later in this class. And back when I was doing it only, let's say, 5 years ago, I was using TensorFlow 0.x, and I can tell you it was way more work than just writing these two lines of code here. So what do? When we have words that we need to represent, for instance, we want to do sentiment classification of words, we have, let's say, I am hungry, and we run it through a word2vec model that is pre-trained. There's some word2vec models available that has been pre-trained on the whole of Wikipedia. So we get a vector, etc., for every word. Using these vectors, then we can do our actually second task, which could be sentiment prediction or not, and we do our actual prediction. So if we're using pre-trained models, it gives us a function here to go from a word to an embedding, and these embeddings we then use in any type of predictive model. When we're doing it in Python, we're using GenSim. So from the models we load word2vec. There's other models available. Word2vec, we say the embedding size, the context window size, the minimum count, so words need to appear at least twice in the vocabulary. That's it. This has to do with parallel training. That's pretty much it. You feed it the documents, of course, and then you can train the model. There we go. So again, you feed it the documents, you train it for, let's say, 10 epochs. That means you go through the entire data set 10 times. So sorry, you don't feed it documents here. You feed it, you say the total examples that you use is the length, the number of documents that there are. Okay. That's pretty much it. We will be working with word2vec embeddings in the lab, and I'll get back to pre-trained models in a little bit. So that brings us to another word embedding model, GLOVE, or Global Vectors for Word Representation. This paper on GLOVE, this is the original paper, came out just before word2vec. And GLOVE is actually a very efficient model. We'll compare the two in a second. I'll first explain or go into details a little bit about how GLOVE works. GLOVE basically combines elements from the two main word embedding models which existed at the point in time when GLOVE was proposed, which was not word2vec. Word2vec didn't exist yet. So they were talking about global matrix factorization, meaning looking at the whole corpus the whole sentence or document, instead of looking at only the windows-based methods. Okay, so matrix factorization, similar to singular value decomposition, is a technique of matrix factorization. Okay. So GLOVE combines the elements of both the global and the local context window methods. Okay, so instead of learning the raw co-occurrence probabilities, GLOVE actually focuses on learning the ratios of these co-occurrence probabilities. Now, how does that work and why is that important? So, suppose we want to study the relationship between two words which are ice and steam. We can do this by examining the co-occurrence probabilities of these words with various probe words. So that'll give us some insight into what they have in common or what they don't have in common. So to do that, we look at the probability of word J occurring in the context or given the word I. So suppose we're looking at ice and steam here. If we're looking at the probe word water, it wouldn't give us a lot of information because water would appear both ice and steam. Okay. For discriminative purposes, you'll need to use a more insightful probe word such as solid. Solid would allow us to find a different relationship between ice and solid and steam. Solid and steam you don't think would appear together often. So for discriminative purposes, we can say that it doesn't give us a good idea of how far apart steam is from ice if we just use the probe word water. So words that don't help us distinguish between I and J, probe words, are referred to as noise points. And it is the use of the ratio between the co-occurrence probabilities that helps us filter out these noise points and focus on the more relevant probe words. Let's look at an example. So here we're interested in both ice and steam. And ice and steam, we're looking at probe words, K, and then we're looking at the final ratio which GLOVE will be taking into account. So given that K is solid, gas, water, or fashion, okay, we can have a look. So the individual occurrences don't tell us that much, right? It tells us that water occurs more with both ice and steam. Fashion, low probability of occurring with both words, so they're not distinguishable. There's some difference here, but what does it tell us? It gets more interesting when we look at this ratio. Now, the ratio basically explodes when we're looking at solids, meaning that ice and solid are way more related than gas and ice, for instance. Because this is a very low ratio, again, which indicates that gas and ice are sort of opposite or not related. Actually, it goes even further, and it allows us to say that gas and ice are less related than gas and steam. Okay. Because if we're using probe words that are not related to either of the words in our ratio, then we get something that is much more close to zero. In the case of fashion, fashion and ice, fashion and steam wouldn't occur. It doesn't tell us anything about ice and steam. If it occurs together with fashion, it wouldn't occur together. Water, they both occur. It's higher than zero. It's a little bit higher than fashion, but it's related to both. So it doesn't tell us much in that regard. But it is the difference here and the huge value here that it gives us the information that solid and ice are way more related than steam and solid. So these kinds of ratios is what the GLOVE vectors are based on. So the final function to train the GLOVE model is considerably more complex because it's an optimization that least mean squares that aims to directly reduce the difference between the dot product of the vectors of two words and the logarithm of their number of co-occurrences. Okay. I don't need you to know the mathematical details of this model, but it is important to know that GLOVE has a fairly fast training. It is scalable, just like Word2Vec. It has good performance. It is even easier to parallelize because, as you know, neural networks, we can't always parallelize the training. But it has a very comparable accuracy than Word2Vec. And basically, based on the previous table, we can see that the ratio of co-occurrence probabilities can help us encode meaning. Now, for some fun graphs, how do we evaluate word vectors or word embedding models? We can do two types of evaluation. First, we can do intrinsic evaluation. How much do these embeddings encode semantic information? Similarity. And extrinsic evaluation, so how useful is it for other tasks? So as I was mentioning before, if we have a sentiment analysis task, using these word embeddings, how much does it improve our task? But first, let's talk about intrinsic evaluation. Let's have a look at a word similarity task. So one cool thing that Word2Vec or Glove or any of these models offers is the ability to calculate similarity. Now, similarity can be expressed in a number of ways. It could be the Euclidean distance between two words. In that case, small distance is a high similarity, or it could be the cosine similarity between two words. You're all familiar with the formula for Euclidean distance, but the cosine similarity often is given as, let's say, it would be given as the length of one vector multiplied by the length of the other vector times the cosine of the angle between the vectors. And what that basically tells us is if the two word vectors are angled in the same direction. Okay, so both similarity metrics are used a lot and can be useful. So in this case, a human has annotated, for instance, that tiger and cat have 7.35 similarity. Tiger and tiger have 10 similarity, so that tells us that 10 is the maximum here. Book and paper, very similar. Plane and car, a little bit less similar, still mid-similar. So we get a similar result if we just use a similarity function of Word2Vec here. In our pre-trained GenSim model, we can use a similarity function, input it two words, pretty and beautiful, and it'll tell us how similar they are, which is a quite cool function, and we'll experiment with this in the lab. If we're looking at how word similarity tasks, how well these embedding models perform on similarity tasks, I found this table in a paper from Pennington in 2014. And we know most of these models now. We have singular value decomposition, some variants of them, continuous bag of words, so that's Word2Vec, Glove, and we see that the best performing model, not surprisingly, given that this was in the Glove paper, the best performing model in the terms of similarity task would be Glove. It is very tightly followed by singular value decomposition. These are just different data sets. And continuous bag of words, this performs quite less. Singular value decomposition here seems to perform best. You must take into account that everything here depends on what data set the models are trained on, what parameters are used in the models, what is the embedding size. Perhaps Word2Vec performs equally well if the embedding size is twice the size, or if smaller data set is used. It can all happen. So I must say that if ever you're making sort of comparisons between models, you need to make sure that you have optimized all of the models and not just the model that you are trying to prove, because that wouldn't offer a fair comparison, but yet it is what we so often see in scientific papers. All right, so Glove, if we find the nearest words in this multidimensional vector space to frog, we see frogs, okay? Toad, Litoria, and then some others. I had no idea what the others were, so I added some pictures for your convenience, and it seems that they're all quite related to frog. Now, another cool way to evaluate our word embedding models are through word analogy tasks. Now, Word2Vec has really popularized this analogy task, I must say, especially if we see the next slide. You might look familiar to you. In Word2Vec, what they've done is again, we have T's and E projections to two-dimensional space of our multidimensional model so that we can have a look at what we're doing. If we have a vector for king and we have a vector for queen, now to move from king to queen, we need to do a transformation like this. If we apply the similar translation to the vector for man, we see that we end up roughly at where women is. That is amazing, right? So you can do the maths of this. We have king minus man plus woman would bring you to queen. If we go king minus man, yeah. So that's quite wondrous. And there's many other examples from the original Word2Vec paper, actually, which is, this is our man-woman example. We have from walking to walked, from swimming to swam, a similar translation. Same thing that we found for countries, capitals. Same this is not the vector space, but it basically indicates that you go from Italy to Rome, from Germany to Berlin, you have a similar translation. That is amazing, and it means that this word embedding model captures the semantic meanings of words, not just in the position of the word, but in the translations between the words. Now this is for Word2Vec. We see similar analogies for the Glove model, man, woman, hair, hairs, sir, madam. It is not exact, right? That would be amazing, but it is not that far off. The same thing works for superlatives, right? Slow, slower, slowest, short, shorter, shortest, similar translations, which is quite hard as a researcher to find these sort of things, but it is amazing that they managed to prove it. Okay. So whenever you're training an embedding model, this would be one particular way of seeing both the similarities and the analogies to see if your vector model actually captures some of the properties of your data set. Now let's move on to the second form of evaluation, the extrinsic evaluation. So now word embedding models can be used as part of speech tagging, for instance. We have input word embeddings are cool, which is a sentence. And the output would be the grammar positions of each in the sentence. And to calculate, to train this type of model, what we do is we replace each word with their embeddings, feed these embeddings to a neural network of arbitrary depth, and to get grammar, noun, verb, adjective. Okay. Now in a more complex form, these networks will actually be LSTMs or RNNs. We'll see that later on, and we'll have a series of these words so that we take the order of the sentence into account as well. That for later. Another task would be named entity recognition. Nous sommes Charlie Hebdo. This is from last year. It was relevant last year, 2 years ago. I have some other problems right now. And in this case, we just say it is, what is it? It is a person. Each word is a person, or it is not a named entity. Okay. There are many applications for data science. So we can input to other models, and we're going to actually be doing that in the lab, where we're going to be using word embeddings for sentiment analysis. To introduce sentiment analysis a little bit to you, so we're prepared for the lab. Sentiments are feelings, affects, emotions, likes, dislikes. Often we represent emotions on a scale which is valence arousal. Valence and arousal. It's actually typically a quadrant scale. And valence would be positive emotion, whereas arousal means energized. And there's some people who say that in this continuous model, we basically can put all of the other emotions in there. Now, we often see in sentiment analysis, especially in NLP, a little bit more of a binary model, likes, dislikes. If you do sentiment analysis of tweets, sometimes they're classified on do they have a smiley face or a frown face, because simply we don't have labels always, right? Okay. We sometimes refer to sentiment analysis as opinion mining, and it can be useful for all sorts of tasks, stock market prediction coming to mind, but many other. Let's say, actually, don't know if I put this in there, so let's wait for a second. If we have the types of sentiment, we can, as I said, we can have binary sentiments, we can have multiple categories with neutral, or we can have a whole scale, okay? Or we can use something like our valence arousal model. Okay. Before you do your task, have a look at how to best represent your output and what you need to know. Some colleagues of mine did a quite cool project where they did a form of sentiment analysis on tweets. It was election time, sort of like right now, and what they did is they analyzed all of the tweets that had the tag, this was Belgian elections. For each party in the Belgian elections, we have a lot of parties. In fact, our government now consists of 7 parties that formed one huge coalition. Again, that aside, this political barometer, the project was called, was doing NLP to predict the sentiment of each of these parties in today's social media, which I think is a very cool project. Actually be worth checking out something similar at the moment. These are some 4-year-old statistics that I found from Trump versus Clinton. I should really be replacing that. We basically show our sentiment of each candidate over time based on some tweets that they found on the internet. So actually, let me see if I find this year's example of something similar. There we go, found it, that was quick. So these kinds of things can give us useful insights into important political sentiments, what's going to happen in our economy, market overall. How are people feeling towards COVID or not? Are they feeling positive towards lockdown measures? Are they going to refuse lockdown measures, etc.? There's a ton of applications for sentiment analysis. So I list a few other applications here of NLP. We could do brand analysis. We could do benchmarking of products and services. How will a new product be perceived, or is a new product perceived? When we're looking at the social media, what's the general opinion about hot topics, COVID being one, for instance? We can use it to determine ad placements. Perhaps we want to place an ad about, let's say, Tesla cars when somebody talks positive about Elon Musk. Okay, so using the sentiment analysis, you can really get an insight into what people are feeling about things. Okay. Right, so traditional approaches includes using things like SentiWordNet. So we talked about WordNet before. It's a more traditional approach to how to represent words and their relationship. In SentiWordNet, WordNet is extended and 3 polarities, positive, negative, neutral, is added. And each word basically gets this sentiment. That is traditional. Way more popular now is word embedding based. So that's what we are going to be exploring. In essence, we have a classification problem. We are going to be doing sentiment label prediction from tweets. The classes that we will be predicting for are neutral, positive, and negative. Now, we can use any classification algorithm that we saw a bunch in our classification class, or there's neural networks always, but we should be clever about the input. Right? Do we use a one-hot encoding, SVD, bag of words, term frequency, IDF? Or do we use something like word vector embeddings? Okay. Let's explore the latter. If we use word vector embeddings, we always do some pre-processing with NLP. So we're removing NLP, non-English words, do some spam detection, remove code, weird characters and tags, etc. That's actually sometimes the hardest part. Also in the lab, this is the most confusing part. Then you tokenize your tweet, tweak or your document, which is basically word 1, you split it into a list of words, which would be tokens. Okay. So now you have, our input is a list of words per tweet. Now we can get embeddings for each of these words, so we're going to be replacing these for vectors. Now remember, there's people out there who have trained GloV and Word2Vec on corpuses of the whole of Wikipedia. So we're not going to reinvent the wheel, we're just going to use their pre-trained models. Okay. So the problem here though, now that we have these word embeddings, is for each tweet we have a vector of vectors. So if we want to be advanced, we will be taking the word order into account using something like attention or transformer networks, a recursive neural network. We will see that in the next week, but I want to just focus on a very basic approach here. So one way, because this is a variable length vector, there's multiple ways of dealing with this, right? One is make them all a fixed length by saying the maximum amount of words in my tweet is 100, and whenever my tweet has only 80 words, so I'm just going to pad it. Just put like NaN characters in the end to fill it up. Then we can feed fixed vectors to our classification method. This is a very good approach. Okay. So we can use RNN or attention as well. It's a slightly more complicated approach. But the very simple idea that you might have is, why don't I take the average position of all the vectors? So basically summarize the vector positions and divide it through n. Okay, we can definitely try this. So if we have our average or aggregated word vector here, so I love the elections, which definitely might not be true. So we go from the words to the pre-trained embeddings. So now they're all vectors. Average these vectors to get the average position in our embedding space of this tweet, and then we classify. It's a very basic approach, okay, but it does not work super well all of the time, yet a lot of people still use this approach. Okay. A slightly better solution would be to use something called document vectors. Okay. Before we get into document vectors, let me retrace my steps a little bit and show you how this is done in Keras. So if we have our natural language toolkit, we can download a punctuation dataset, and there is we create a function to tokenize our text. Okay. Basically using the English language, because we do a check if everything is really English, and the English language is actually downloaded when we do our punkt download. We tokenize for every word that exists in the language dataset, we tokenize it into our token list, and we return the tokens. Then, as before, we do a training test set split of our entire dataset. It is 30% of our data is going to be used for our test set here. To the test set and the training set, we apply the tokenization function. That is basically it. Okay. This will be explained in the lab in more detail, just wanted to show you already. So once we have our tokenized training set, we can average them, feed them to our classifier. An alternative here, which I don't actually go into details in the lab, would be to use the entire joint vector as an input. The problem might be that your model requires a lot of memory and will become sparse. Also, this needs to be a fixed length n, so which might require you to do some padding with empty values. Okay. Oh, there's a Python function here. Basically, you can take the mean of all of these word vectors. You could also include the variance if you'd want to be creative. And GenSim will allow you to then just use this mean vector instead. So somebody thought this might not be a good solution, so there is something called document to vector, which basically is going to learn an embedding for the whole document. So one embedding for the whole document or tweet here, which can then be fed into our classifier. So document to vec, we're not going to go into too much details, but when we train the model, it works in a very similar way, except that we always feed it a paragraph ID or a document ID. And this paragraph ID, which is treated as an extra word when you train the model, will allow us to learn these properties per document. And all of the words are fed at the same time as well. It provides a fixed length vector here, which is exactly the embedding that you will use when you're going to be using the output of your document to vec model. Okay. It is called a distributed memory version of paragraph vectors, but as I said, this is just for your information. We are not actually going to be looking at this in detail. So the paragraph vector really, when we're training the model, it's concatenated or averaged with the local context word vectors to predict the next word. And this prediction task changes the word vectors and the paragraph vectors to become one document vector. Okay, so what's important for me is not so much that you can tell me the mathematics of doc2vec, but that you know that it exists. It is an option for you to explore and you can implement it. This is an exercise we'll do in the lab. So when we're actually implementing this, what we need to do basically is we need to add a label, this paragraph ID, to all of our documents or tweets or whatever. So here's an example function that we can do this, basically adding this label, okay, which returns us a new labeled dataset. So for the rest, a lot is the same as before. In Keras, we now can build a doc2vec model which feeds in, which takes as input all data when it is actually trained. Okay. It's a little bit more complicated to train this model because we're not using GenSim for this particular one. We're first defining our doc2vec model with the embedding size, minimum count for all of the words. Alpha is just learning rates. Then we say that we build our vocabulary. And once we have defined our model and our vocabulary, we can then for each epoch train the model. We shuffle all data. We use all the data for one epoch here. We use a learning rate, and that is all there is to it. Then we can get the learned vectors based on the whole for each entry of the training or test set. And each of the outputs will be 300. Okay. Once we have document to vec, we can basically see that we can now make a TS&E projection, remember TS&E, of not just words, but of entire documents. So there's a paper from 2015 who's created a document to vec model for every Wikipedia page that exists. Now, that's interesting because once you create this embedding for each Wikipedia page, then you do a projection of this page using TS&E, you can see that similar pages on a similar topic are grouped close together. That is an indication that this doc2vec model works. You see, for instance, all Wikipedia pages about music albums are here, films, computer science, species, animal species. So athletic sports are a bit more dispersed, but still there's clearly a pattern to be seen, and this is something as part of the intrinsic evaluation that our doc2vec model works. Whenever you're using a pre-trained model, you should actually take care that you use a pre-trained model that is trained on similar data. So if you're going to be using Twitter, it's a very different speech than Wikipedia, or if you're going to be using text as a mass language, it's very different from news articles. Okay, so train on a corpus that represents your data. Also from this Doc2Vec paper, we look at the cosine similarity between the page for Lady Gaga and similar pages. You see that there's a high similarity with all of these singers. So it's faster, consumes less memory than Word2Vec, typically obtains better results, and we will do a comparison about Word2Vec versus Doc2Vec in the lab. So that was an example of how you could do text classification. We will be talking more, especially with Professor Janja, on NLP in other classes. You'll be using 1D convolution, for instance, to do your word representations as well, but this is serves as an introduction. So things that you will use is the NLTK toolkit, the Natural Language Processing Toolkit in Python. Google Cloud NL API is also a very good one to check out. And I should stress that you don't want to reinvent the wheel. Use pre-trained word embeddings. There's a few links for you. All the popular libraries include these embeddings, one command to load them. Here in GenSim, previously the code example I showed you does a training of the model based on your dataset. But you could just do load Word2Vec based on some Google News data, which is actually, I think, gosh, I don't know how big it is, but it's millions of news items. So it's way better than you probably are going to be able to do. Glove also has some pre-trained embeddings, and so does the link there, the dependency-based, skip-ram-based models. Now here's a little bonus application for you. You can also apply Word2Vec to music, which is something that I've done in my research. Now, I noticed that Anna Huang, which is a friend of mine, has applied Word2Vec to chords. And actually, Anna Huang, you might know her. She was the one she works for Google, and she was the one that created the Bach doodle, the music generation doodle on Google a while back. She's a very cool trinket. So Anna Huang said that chords might be represented in a Word2Vec model. The cool thing is that once she created this word embedding model for chords based solely on their co-occurrence, so she just fed the model songs represented by chord sequences, she found that in this embedding space, we find something called the circle of fifth. Now, if you're a musician, you'll know that this circle of fifth here represents transitions that are usually well-sounding. So if you're playing a C chord, going to a G and a D is very natural. Okay, going from a C chord to A minor, very, very closely related. So, and in this Word2Vec space, again, this is a T's and E projection, this circle of fifth comes above. So this is very cool. Right, so what did we do as a follow-up on this work? Well, we looked at complex polyphonic music, which is music that looks like this. So in this complex polyphonic music, we just sort of decided to slice our data, the boxes you see here, and each slice was just replaced with word 1, word 2, word 3. So the model was not given any information about what is in these musical slices. So these musical slices become words, and then we do the exact same approach as how to train Word2Vec. We had 130,000 pieces in 8 different genres. Often music research constrains to one particular genre, but we decided to do all of the genres at once. And the results were actually quite encouraging. So without knowing which notes are in these slices, we actually see that the model learns that tonally close chords have a low distance. And that is reflected in the similarity matrix here, which lists the cosine distance between different chords. Okay, so the chord labels are here. And we see, for instance, okay, the cosine distance between a chord and itself is 0, which is on the diagonal. A chord, then let's have a look at 2 related chords, let's say C and G. C and G, which we find here. they have a high similarity. They're 1/5 apart, which means they're very often played in the same context. Okay. Let's take another example. Basically, these chords are ranked according to the circle of fifth on my axis here. And we immediately see that adjacent chords are more similar. So again, something about this circle of fifths that is so important in music theory is learned. And if we plot the cosine, the angle between the vectors, again, we see that they have similar angles, thus creating a multidimensional circle of fifth again. Now, how do we go from chord slices to chords for each of the slices that we have afterwards in the analysis? We created an algorithm to get the nearest chord, so maybe G minor. So using all of the slices and their chord label that we added afterwards, we find this graph. So it was quite a lot of data mining to find interesting things from our data. We also found that 1 to 5 chord vector angle reflects this circle of fifths. So that is exactly what we see here in this graph. We also see how the distance between chords and the C chord here, so 1 in the numerical values, the distance between 1 and all of these other chords here over the course of training the model evolves. So we see that the blue one, the G major, is the fifth, which is very important in a key, becomes a lot smaller. Okay. Then we see, for instance, that the distance between, let's say, the red one, the fourth, also becomes very small. Then we have A minor. If you're a musician, you'll realize that this is indeed an important conclusion. What doesn't go down so much is the purple one here, which is the D flat major. And indeed, if you're playing a C chord, D flat major is not something that would occur often. So why am I saying all this music? Just to show you that word2vec, without knowing what was in the words that we gave them, just by looking at the occurrences, just like in language, was able to model the semantic content of the music. Now, if you're more interested in that, check out our ArcSIF paper, or actually published paper in Neural Computing Applications Journal. So this is a very promising approach to modeling music, but many other things as well. Now, to round off this lecture, in NLP there have been some evolutions in recent years, and I'll leave it to Prof. Sujanya to go into more detail on transformer and self-attention networks, but I just want to mention the names. They're all very Sesame Street related. We have Elmo in 2018, which is basically a bi-LSTM model, which takes into account the entire sentence before assigning each word to an embedding. Okay, so you can't just feed it one word, you have to feed it an entire sentence. Then we have very popular the BERT model, which is a transformer, bidirectional transformer, which implements self-attention blocks. What do self-attention blocks do? Basically, if you have a sentence of words, basically if you're representing a word and you know the surrounding words, self-attention is going to learn how much to focus on the previous words, so it learns weights for this in its attention mechanism. So how much to focus on words that are further back in the sentence or not. And this is what we call self-attention. And within the transformer network, this attention mechanism plays a very important role in both the encoder and the decoder. Okay. So a very nice way of thinking about attention is, if I look at the room, imagine I was standing in front of a classroom, I look at the classroom and I'm talking to one student. My vision field is picking up everything, but I'm actually focused only on one student, so I'm not processing much of what's happening around me. So that's exactly how the self-attention network works. It's going to be focusing on the words in this case, or the features that are important for me depending on the task that I'm doing. Now, more details in another lecture, but this BERT model is often implemented end-to-end as a translation model. So, for instance, here, I like cats more than dogs. Input sentence, we have attention, encoder and decoder, and outputs the translated sentence. So you let me know if this is correct. I think it's Japanese sentence. It can also tell you how similar two sentences are. Recently, transformer network was adopted to not just do n to n, but also n to 1. So in that case, it could be used, let's say, for sentiment prediction. In fact, in a recent paper of mine, I'll put the link here, by my PhD student Tao, we used transformer networks to predict the sentiment of movie clips. So the input here was a bunch of pre-trained models, ResNet 50 scenes, VGG-ish, trained on audio. And all of this, we used the attention network to focus, to see which features we should focus on. And then that predicts us this valence and arousal value of the resulting movie. Okay. Our model was called Attend Effect Net. It was just published to ICPR. So if you're interested, you can look that up. Now, pre-trained BERT embeddings are very popular, and I'll leave it to Professor Janja to go into more details on BERT. Some of the references for this lecture. I'll see you in the lab where we're going to be practicing different types of embeddings, how to do sentiment prediction, and how do we train our own word-to-vec and doc-to-vec models. Hope you enjoyed the lecture.